in Math 206, you might have noticed in your homework that when you compare two linear measurements for two similar figures, then their linear measures have a scale factor. Like you multiply the side length times k to get the side length of the other figure. Now, if you have polygons that are similar, then they, with scale factor k, it turns out that the ratio of their areas is k squared, which should make sense because it's a two-dimensional type of measurement. And then with that in mind, if you compare similar figures that have scale factor k, then their volumes have ratio k cubed. So let's think about this, and you'll have like a lot of homework problems with which ask you to compare similar figures by looking at their ratios of their areas or volumes or whatever. Let's look at this example. Is it true that the viewing area of a 35-inch television screen is about twice the viewing area of a 25-inch television screen? So a few things we need to know. What does it mean to have a 35-inch television screen? And also, these things are measured diagonally. And also, what do you call the viewing area? Would that be the area of the screen, so the area of that rectangle, right? Right. And the other thing that we should know is that all televisions should be similar rectangles, meaning the ratios of the sides are the same. So let's draw in two such televisions. Let's say this is my 25-inch screen, and this is my 35-inch screen. Well, what's the scale factor from one to the other? Well, the scale factor, K, would be the ratio of 35 to 25. Which is approximately or exactly 1.4. So now what would the area be of this rectangle compared to the area of that rectangle? Well, that we know that the scale factor, if the scale factor is k, the ratio of their areas would be k squared. So if you do 1.4 squared, you get 1.96, which I could say is approximately 2. So is it true that the viewing area of a 35-inch screen is about twice? Yeah, it's because the scale factor for the areas, so the area scale factor is k squared. So that's approximately twice. Let's now look at this next problem. How does the surface area of a sphere that has a 10-inch diameter compare with the surface area of a sphere with a 5-inch diameter? And now you have to remember that all spheres are by nature similar because they're such symmetric objects to begin with. So here, if the linear measurement, here you've got a 5-inch diameter on a small sphere and a 10-inch diameter on the large sphere. The scale factor here, the linear scale factor, K, is 2 because the larger diameter is twice the smaller diameter. So then the surface area scale factor would be k squared, or 4. And you can check this by actually calculating the surface areas. We saw from last time the surface area for a sphere would be 4 pi r squared, right? So here the radius is 2.5, and here my radius is 5 inches. So the surface area of the large sphere would be 4 pi times 5 squared. And the surface area of the small sphere would be 4 pi times 2.5 squared. So now if you make the ratio of those two amounts, large over small, what you would get is the 4's cancel, pi's cancel, 25 over 2.5 squared, which is 6.25, and 25 divided by 6.25 is indeed 4.